24, question 44. A first order heterogeneous reaction A to B is carried out using a porous spherical catalyst. So this is my porous spherical catalyst, and this is the bulk gas surrounding. So this is the bulk gas surrounding the catalyst. Assume isothermal conditions, so assuming that the temperature here is constant, and I assume that the temperature on the surface of the catalyst is also constant at Ts, and that interphase diffusion controls the reaction rate. So basically we are assuming that here interphase diffusion means that the diffusion inside the pores is that means from the bulk from the top from the surface of the catalyst particle going inside the pores. So this is the network, assuming this is the network of the catalyst pores. So that is the controlling resistance. We'll go into the data later on, but let's see what are the steps involved very quickly. First, of course, is the external diffusion, where the bulk gas from the bulk gas, so let's say it's a mixture of gases, from the A component from the bulk gas goes to the surface of the catalyst. So that's my part 1. Part 2 is interphase diffusion. From here, let's say this component A or the reactant goes inside the catalyst pores all over, and there are active sites, absorption and reaction on active sites. So these components, the reactants gets absorbed on active sites, and then there's a reaction happens. After the reaction happens, the products on reactants and the products come out from the pores, and they again go back to the bulk of the gas. So these are the normal steps of a heterogeneous catalytic reaction. That there are 2 cases. In case 1, the bulk concentration is given and the catalyst particle diameter is given. This catalyst particle is given and the bulk concentration is given, and the observed reaction rate is given, which is 0.2 moles per second per liter of the catalyst. That means catalyst volume. The question is, if we change the bulk concentration here, bulk concentration is changed, and if we change the catalyst particle size, then what would be the rate? So that's a question. Now before that, let's go to a very quick summary. Okay, very first one is let's call this as an effectiveness factor. Let's call this eta as an effectiveness factor. That is normally defined as the actual or the observed reaction rate divided by the reaction rate. This is the hypothetical one. If all the internal pores of the catalyst are exposed to Cs and Ts. So we know there's a difference in concentration because this is the concentration Cs, and the reactants have to go inside the catalyst pores, and while going here there is a concentration gradient. Okay, so there is a diffusion inside the catalyst pores. So if we assume hypothetically that the entire all the catalyst pores, all the sites are or can see the surface concentration or available at the constant surface, that means there is absolutely no diffusive resistance inside this one. Okay, so if that is so, then what will be the rate? So that is a hypothetical rate. So the actual divided by if the entire catalyst pores are available, and they can see the surface concentration. So in that case, so that is this ratio is called the effectiveness factor. So here, if we integrate this one, the rate of reaction in concentration and temperature at different points here, and multiplied by the dV, volume of the catalyst, divided by the actual volume of the catalyst, and this is the rate of reaction at CAS and TS. Okay, so that's the formal definition of the effectiveness factor. Now, beyond that, let us quickly see what does this effectiveness factor means. So this is my effectiveness factor. Effectiveness means that if let's assume eta is equal to 1. Let's assume eta is equal to 1. What does it mean? That the actual observed reaction rate is the same as the reaction rate where entire catalyst particles can see the CAS, and of course the temperature remain constant. That means there is no diffusive resistance here. So no diffusion limitation exists if eta equal to 1. So eta equal to 1, no diffusional limitation. Okay. Alright. Now let's assume that eta tend into 0. What happens if eta tend to 0? That means this is equal to 0. Okay, what happens? That means here the catalyst ports are starved of actual reactant going through this one. So what is happening? There is hardly any component A is diffusing inside. That means a severe diffusion resistance, right? So eta is equal to 0 means severe diffusional resistance. Eta is equal to 0, severe diffusional resistance. Okay, and if eta is less than 1, that means basically this is very high. That means what? That means the diffusion limitation exists. This is very high and this is small. So the actual reaction rate is small means that means severe diffusion resistance exists. Okay, so eta less than 1 means the diffusion, eta less than 1, diffusion limitations exist. Okay, and if eta can eta be greater than 1, yeah, this can sometimes happen at least for exothermic reactions, so that may happen also. Okay, parameter, this is called Healy modulus. So these all definitions are, of course, are given in Octave 11 tool, and I'll just discuss that and HS Fogg there. So I'm taking all this information from these two books. Okay, so now let's look at this Healy modulus. Healy modulus is defined as the intrinsic reaction rate divided by the rate of interparticle diffusion. So what it means, if let's say phi is much less than 1, that means what? If this is, that means this is very high, rate of interparticle diffusion is very high, that means that's particles, that means that the A can diffuse through this pores very fast compared to the reaction rate, intrinsic reaction rate. So phi less than 1, that is basically phi less than 1 is basically called kinetic control regime or intrinsic kinetics control. Just the opposite, if phi is much greater than 1, then what happens? That means this is very high compared to this one. That means the reaction rate is extremely high, and the diffusion cannot supply the reactant fast enough compared to the reaction rate, right? That's why what happens, phi greater becomes much greater than 1. That means that the concentration of A inside the pores is approximately equal to 0. Right, and this is called intraparticle interphase diffusion control. Interphase diffusion resistance controls. So our problem is in this range. That means phi is much greater than 1. Okay, so given these things, let's quickly see what are the relationships. I'm taking this from Levenspiel book. So here, this is the reaction rate overall, or the observed reaction rate. This one is basically the intrinsic kinetic reaction rate, and this is my effectiveness factor. So if silent is, let's call it as eta, the way we have defined before, and we have defined eta for different geometries. This is for the sphere, which is applicable to us. And this MT, which is the Healy modulus, which we define as phi, and I'm writing 1 because assuming first order reaction. So Thiele modulus for a first order reaction. So that is defined by this particular relationship here, where L is called the characteristic length, and this is equal to R over 3. That is also given in Levenspiel, page 386. So phi 1, the Thiele modulus for a first order reaction, is R over 3 root over K over dE, where d is the effective diffusivity, and this of course is the kinetic rate constant. So the observed reaction rate would be equal to concentration of the bulk, assuming, so the bulk concentration, assuming there is absolute no diffusional resistance inside the bulk. So the concentration here and on the surface are pretty much the same. So if that is so, we can say that for this particular case, when phi is greater, when MT is phi here, when phi is, as we discussed, much greater than 1, around this value, you can see that eta is equal to 1 over phi, right here. Effectiveness factor is equal to 1 over Thiele modulus, okay? When phi is much greater than 1, okay? So if that is the case, then we just substitute here, this one to here, and this is the relationship we get. So this is my effectiveness factor for sphere and for first order kinetics, and of course interphase diffusion control regime. Okay. Alright, if that is so, so after substitution we get this particular relationship here. Okay, these are details are given here. So as we can see that the observed reaction rate under this situation, that means under the interphase diffusion resistance regime, we can see that the rate or observed rate is going to be directly proportional to the bulk concentration and inversely proportional to the radius of the particle. So now it's just a matter of substituting the values, and this is going to be my answer. Okay. Now, very quickly, I just want to show you that the Fogler also give the same thing. So this is the definition of the effectiveness factor as given in Fogler. And here, this is the modulus, Thiele modulus as given in Fogler. So this is my interphase internal diffusion limited regime, and the problem really is referred to in this particular regime right here. So under this situation, the rate of reaction is the same as we have discussed just in the previous slide. So it's pretty much the same equation whether you go by Levenspiel or by Fogler. So that pretty much ends the discussion on this particular problem.